Okay, it's my great pleasure to give you an overview on the global impact of solar PV as a central core of the Power-to-X economy. And the brief agenda is just background, then a global view on 100% renewables, a perspective from Europe, and then a summary. First of all, let's start with a background, why we have to be very fast in the energy transition, and this is due to climate change, among other challenges, but that's really very dramatic. We are at the peak of the emissions as of now with 40 gigatons in the world, and we have to be faster than 2050 if possible at zero, and then for various decades on massive negative emissions. And the reason is the carbon budget for 1.5 degrees Celsius, as all countries, almost all countries in the world have agreed on in the Paris Agreement. This has been already used the one or the other year in the past. And the reason is if we take a high probability of reaching the target, including uncertainty, as then the budget is already used, so there is no budget left. We're already in the deficit. The consequences, we have to transition as fast as possible. So this is a rather desperate situation, to be honest. That means we need solutions. Luckily, we have solutions, and let's focus today more on solar PV, but I will not fully ignore other renewables and other options as well. However, the key drivers for the transition will be availability, electrification, and cost. Let's start with availability in the top left corner. There you see with this orange bubble, what is the primary energy demand in the world today or around about today and 2050 compared to what resources we have. Do not care too much on the numbers, on the units, on the numbers, but not on the units. All in all, we have 1,000 times more solar irradiation in the world per year than what we need as society. In addition, we have several times more wind and, of course, all the other renewables, ocean energy, bioenergy, hydropower, geothermal. So first of all, we have not an energy resource challenge. That's the best news of all. Then electrification, the more we go for direct electrification, the better it will be. Also, not only from energy efficiency point of view, also from cost point of view. This is with power generation. So if you have thermal power plants, they have on a global average fleet 35% efficiency. When we harvest renewable electricity with hydropower, wind turbines, solar PV, then this is almost 100% primary energy. Just from the definition of primary energy. Heat is very similar. If we burn something, we are close to 100% heating efficiency for space heating. With heat pumps, we have a factor 3, 4 in between. And when it comes to mobility, if we have a combustion vehicle, then maybe cars on annual average have 20% efficiency. Maybe with trucks, we're a bit better, but anyway, it's low. However, with battery electric vehicles, we have a systemic efficiency of 70, 80%, again, factor of 3. So whenever we can go for direct electrification, this is the way forward, also in cost. Let's come to the cost, bottom left. So this is a diagram original from the International Renewable Energy Agency, however, also adopted by the IPCC. And what you can see there is a very simple economic rule. The more we build of something which is modular and standardized, then we get the cost down. And this is in particular the case for solar PV, as you can see in the last 20 years, more than minus 90% in cost. This is the reason why now solar PV is the least cost source of electricity in the world. But it works similar for batteries and other technologies. But batteries is most important because that supports PV massively. However, where PV comes from, this is not just a new technology of the last few years, as we know. Now it started many, many decades in the past, and with a kind of a market rollout in the 1950s with first space applications, off-grid, even extraterrestrial. However, then with off-grid solutions on Earth, and then on-grid solutions, rooftop power plant, and now I would say large power-to-X plants for e-fuels, e-chemicals now projected and the first to be built. And that leads to a steady growth in the growth rate because the y-axis is in logarithmic scaling. If we have roughly a linear function there, that means the growth rate remains stable. And stable means even from 21 to 22, we had 30% annual growth rate, while from 22 to 23, it was even higher. And there was no, this is the bottom right diagram, never a kind of an energy technology with such a kind of a steep and fast phase into the global energy system as solar PV. So there is already from that perspective something very particular. In 23, we had from the DC units, the annual installed capacity, latest number, roughly 440 gigawatts. And the expectation is towards the end of the decade, 1 terawatt annual installation. Next decade, increasing to around about 3 terawatts a year as a kind of a least cost solution. These are numbers from Bloomberg New Energy Finance the last 15 years, and it's all global power plant capacity, what have been installed, and then normalized to 100%. What we can see 15 years ago, solar was small. In the year 21, solar contribute 50% of all power capacity. And please have in mind what I said before, plus 30% year-over-year growth from 21 to 22, and additional 70% from 22 to 23, and growth will continue. And the reason is extremely low cost. So nowadays, 2/3, 3/4 of all global installed power capacity is solar. All new renewables together is 85%. In some countries, there is a strange discussion on nuclear. Just forget about the zombie technology. You see the red stripes on top. This is not anymore that relevant in the world, except a country want to go for nuclear weapons or maintain a kind of a respective nuclear military infrastructure. Levelized cost of electricity for PV, but maybe let's have some comparison to wind. So where we are in the near future, around 2030, maybe southern part of Europe, it's a kind of a green metric. These are utility scale plants, so around about 20-25 euros a megawatt hour, depending whether it's fixed tilted or single axis tracking. Single axis tracking slightly lower in cost due to a bit better performance. Then 2040, we go towards 15 or below 15 euros a megawatt hour. And in 2050, we would be towards 10 euros a megawatt hour, depending where in the world we are. So it can be a bit better. Just take the best place in the world or side, Atacama Desert. Then it would be really substantially below 10 euros a megawatt hour, but large parts in the world in the Sun Belt are around 10 euros a megawatt hour, and this is then really substantially less than wind, and that enables enormous business opportunities for PV, in particular for e-fuels and e-chemicals, and increasingly e-materials. Solar hydrogen, that was a nice paper just in the recent past. If you really put everything in the green corner for solar hydrogen, with low-cost electrolyzers, low-cost PV, best sites in the world, large-scale utility plants, then you can find, and these are the numbers, there are always 3 numbers per different locations for more or less present, then 2030, 2050. And you can see around 2050 in the world, we talk from 10 euros per megawatt hour, but now levelized cost of hydrogen, up to, let's say, 30 in the Nordics. So this is then this range, and around the Mediterranean, maybe 15 to 20. And that means this is the least cost source, how we get hydrogen, renewable hydrogen. So natural gas-based hydrogen, called then blue hydrogen, cannot compete to that, not at all. And this competition will be already lost around 2030, if not before. Yeah, let's have some global view on 100% renewables. First of all, this is a diagram where all kinds of global 100% renewable studies have been put into. The x-axis is the solar PV share, the y-axis is the wind share, and then you see always first author with years. The green dots indicate it's just the electricity or electricity-based study, and blue means the full energy system. And if studies are around 80-90% line here, then it means 80-90% of all electricity, or even all total primary energy demand, comes from solar and wind together. And then it's quite interesting. We have a kind of a group of studies. They prefer a bit more the wind, and then a group of studies preferring more a bit PV. So my team belongs to this team. It's then Bogdana Vidal, key researcher in my team, and but also several others. So it's 5 different teams that are more in the solar corner. And there may be 2 quite interesting dots, and this is the blue one here from our team, and the other one from the team of Mark Jacobson in Stanford, where solar and wind together reach more than 80% of the total primary energy demand, and this is only possible if you have massive power to X solutions. So everything what can be not directly electrified then to be built on this electricity, but then via hydrogen and other solutions. However, all what have the studies in common where the solar share is then very high is, first of all, they anticipate a continued PV cost decline. Okay, this is now experience for decades, maybe that not surprising. However, in addition, of course, overall electrification is assumed and PV benefits strongly from that. Low-cost batteries are very important to overcome the day-night variability for PV. Low-cost electrolyzers, then PV benefits even more from low-cost electrolyzers, because then electrolyzers can reduce the utilization, and there can be even 2,000, 2,500 full load hours linked to single axis tracking PV, and this is then part of a least cost solution, and generally all kinds of power to X solutions. Now, just a brief glimpse on the model we use. This is the Rete Energy System Transition Model, because it will play a role in the one or the other following slide. It's just a kind of, I would say, standard energy system model now developed for the last 10 years. We cover, it's written here, 150 technologies, maybe 170 is currently the better number. It was used for dozens of studies on all kinds of levels. However, with that kind of model, we can describe all kinds of fossil scenarios, nuclear scenarios, renewable scenarios, whatever are the shares. So we're very flexible with all the parameters. However, it's optimized for one particular application, and that means up to 100% renewables and power to X. And X in that sense means it can be heat, it can be fuels, it can be chemicals for industry, even materials. Just think on green steel. That in the end is based on electricity with green hydrogen, but it can be also other green materials. Fresh water. So if there is a limit of water supply, then with desalination, we get water. CO2 can be captured, and even, of course, for negative emissions, not only for utilization. Carbon dioxide removal, that is on a broader scale, not only with electricity. And we have even power to forests, but maybe I will not go into the details for that today. This is a key study which had been published in a journal just a few years ago, 21, but is based on a report 2 years earlier. And this was the first study showing in full hourly resolution for the world, and the world structured in 145 regions. By the way, Italy is one region of these 145, to show how a transition can be for 100% renewables, and most important, cost neutral. And this is the central diagram here. Levelized cost of energy. Do not mix it up with levelized cost of electricity. So this means really all final energy with the entire energy system cost. And this is roughly a cost neutral transition that, at least at that point in time, was new. However, it requires massive investments. You can see that on the right diagram with the capex, and the lion's share goes to solar photovoltaics, but not only so. We have also investments for heat pumps, for batteries, for electrolyzers, for synthesis units, and of course for wind power, and then quite many stripes for some bioenergy capacity here, maybe some geothermal there, some connection grids here, transmission grids, and so on. So, but all in all, a massive investment. And from the total levelized cost of final energy, let's call it, it's neutral, but it will be increasingly capex dominated. And due to that, the fuel share can be squeezed out. And it requires a massive scale up in electricity. So factor 5, 6 more electricity in the energy system. And this is very strongly based on solar. Please have in mind, so 70% solar is one of the highest shares ever published. However, please have in mind that more than 2/3 of world population lives in the Sun Belt. And there we have the by far strongest additional energy demand for fast rising standards of livings in developing and emerging countries. And summing that up, that leads to more than 60 terawatts of PV. At that time, chemical industry was not yet included. If chemical industry is included, then we would talk on, let's say, 75 terawatts of PV. And of course, a respective number of batteries, so more than 70 terawatt hours of battery capacity, stationary battery capacity, more than 10 terawatt hours of electrolyzers, really huge numbers compared to what we have today. However, what is really the paradigm shift is maybe not that much how we use electricity on the primary energy side. So here you can see it increases from a bit more than 20% to maybe 45%. And the fuel share is declining, in particular, less fuel demand on road transportation with electrification there. Heat rather stable. However, you see a massive paradigm shift on the primary energy side, which is the left diagram, where today primary energy with electricity is just hydropower, some wind turbines and PV, that's it. And the rest is typically fuels. Fossil fuels largely, and that will transition due to cost finally and efficiency, at least if this scenario becomes true, to around about 90% electricity on the primary energy side. And that already indicates you why the title of the presentation is called Power to X economy. We start with electricity and then all final energy demand is covered. So this is maybe the first central point on that. And of course, it's cost driven. Now, let's have a first view on hydrogen. What is the role of hydrogen in a power to X economy? First of all, almost no one is really interested in hydrogen. What we're interested in the end is maybe methane. I would not bet anymore that much on that. Kerosene jet fuel, this is here with Fischer-Tropsch liquids indicated, in particular ammonia, and even more methanol. Methanol might be the most relevant hydrocarbon chemical fuel in the future. And the reason is this will be the basic chemical feedstock for chemical industry, but most likely also the fuel for international marine transportation. And with a methanol to kerosene step, which is efficient, not that costly, we get it converted to jet fuel. And then it's very, very flexible. So that will be large amounts. However, on what we are talking, so we are talking on more than 60,000 terawatt hours of hydrogen. That would require roughly 90,000 terawatt hours of electricity, and this is roughly 3 times the total global electricity generation as of today. So whether we get this ramping realized, we will see. And that will lead to more than maybe 15 terawatts of installed electrolyzer capacity. The current world market is less than a gigawatt a year. So that would require massive changes in the system. Let's have a view on Europe. So the same metric and the logic of the diagram as before. There are not that many studies for Europe where really all is included with a full transition for entire Europe. You see the studies are a bit more moved to the wind energy part, but this makes sense compared to global studies because we have just the strong seasonality across Europe with the winter half year, so a higher wind share is fine. However, there is the one or the other study where it's more than 50% solar. What drives solar? This is again anticipated cost decline of solar PV, and again, of course, batteries, electrolyzers, and high levels of electrification, and PV always benefits from that. There are other studies, they also have higher than 50% of PV, so we're not alone there, so that's quite nice. In particular, this nice study from Mata Victoria using PIPSA, and they did it also for the entire European system. So that's also quite nice. However, and this is maybe the problem, in major reports for Europe, this is practically unknown. And these are typically consulting reports, whether it's from McKinsey or DNY, Navigant, IEA reports, and others. They have very low ambitions of PV, typically 20% or even below. And what are the reasons? Lack of ambition, no 100% renewable scenarios are known for those. A lot of very high cost fossil carbon capture and sequestration, nuclear, low levels of electrification. So maybe they're called consultants, but maybe they need some consulting. And they have oversimplified models, so low temporal and spatial resolution, often not a cost optimization. Sometimes it has appearance whether it was put together with Excel, I'm not sure. So there we need much, much better knowledge levels on the consultancy level. Hopefully they catch up soon. Okay, but now let's have a scenario for Europe where we got the task. Is it possible to have a 100% renewable scenario and at least zero CO2 emissions for 2040 for Europe? And yes, it's possible. You can see this around about 4 gigatons of CO2 emissions in Europe for power, heat, transport industry can go down to zero. It's not absolutely zero, and this is the limestone CO2 part of cement industry, where I think we have to fix it for the time being with carbon capture and sequestration. But anyway, it's close to zero. If it's a kind of a European sovereign supply scenario, so as little imports as possible, then the electricity generation may see a factor 2.5 to 3. So massive electrification with more electricity driven by wind and solar. Cost can be roughly stable. Levelized cost of electricity can decline. Still, we need fuels and chemicals. This is bottom left with sustainable bioenergy, always welcome, and the rest is based on hydrogen, but typically not hydrogen directly. Now let's talk a bit on the power to X economy and sector coupling. As you can see here, this is the energy flow diagram as of today of Europe, of the power demand, industry demand, heat demand, transport demand. On the left-hand side, you see where we get the energy from: oil, coal, gas, biomass, often not sustainable, nuclear, and then renewables. And you cannot see much sector coupling, and you understand what I mean with sector coupling if you see this diagram. This is then a jump into the year 2050 for power to X economy, as let's call it a new characteristic term. The demand is not that completely different. However, the primary energy side is really different. Oil, gas, coal disappeared. Import is just very low, but we wanted to show in principle can be done. Biomass is then sustainable. The number is more or less the same, but it's taken care that it's sustainable bioenergy. Then environmental heat taken by the heat pumps, and the rest is electricity. And it's largely solar and wind, roughly half, but there's some wave power, some hydropower, of course, still some geothermal. And then you can see as much direct electricity use as possible in the power sector for industry, high temperature heat for heat applications, lower temperature heat via heat pumps. Then the environmental heat is induced by these heat pumps. And of course, a lot of electricity directly for the transportation sector, in particular road vehicles, but not only. We can have on shorter distances, of course, also marine and even aviation applications, maybe in 15, 20 years. And of course, most of the railway system in Europe is already electrified, which is of course great. And then you can see hydrogen. This is the blue stripe here. So electricity goes to hydrogen as a least cost solution, but then the hydrogen is largely converted to ammonia, methanol, and kerosene jet fuel. And as little transport for hydrogen as possible is the way forward. Now the question is, can that be a stable energy system? So this is an hourly resolution. Of course, the entire model was done in hourly resolution, Europe in 20 regions. And you can see the best resource week of the year. This is in May. The worst is in November, maybe 1 month earlier or later, but these are typically the times where we have the best and the worst week. And then focus a bit on this orange part. This is called in the legend power to fuels, and that means electrolyzers running, taking up low-cost electricity from solar and wind, converting it to hydrogen within a buffer storage, then going for synthesis units for ammonia, methanol, jet fuel, maybe some methane, and of course some hydrogen is needed for the steel industry, for iron ore reduction. But the point is, you see in May, huge volumes go via hydrogen to other energy sectors in this sector coupling way, while in the winter this is much lower, because then if not generally in the winter, but if you have such a kind of a limited supply with maybe some foggy days, not much wind, solar very low, then these electrolyzers would go out of the system, and we would use hydrogen from a hydrogen buffer storage for the baseload synthesis. And this is then part of a least cost solution. This is the second last slide, just a glimpse on Europe. The left diagram is the capacity. The right diagram is in electricity for all supply. Maybe let's have a jump into Italy, where you see it would be more than 3/4 of all electricity for the country would be solar, because the yellow-orange part is all solar. But still, of course, some wind and some other options. And if you have the overall view on Europe, not surprising, the more in the southern part in Europe, the more solar, the more we are at the Atlantic coast, the more in the Nordics, the higher the wind share. But I think this is what we all know. Let me come to the summary. All in all, electrification is low cost and highly efficient. Due to that, we will see that. Solar PV develops beyond any historic experience of any energy technology. So let's be prepared for new surprises. Solar and wind power are central for a comprehensive electrification, whether direct or indirect. Global, maybe PV would reach 70% of primary energy supply. In Europe, it could be around 50%, 55%. Maybe that's the order. And around about 40% important is wind power, and all other renewables go for the rest. And maybe here and there is an old nuclear reactor running for some time, but new nuclear is really super expensive without massive subsidies. It's no way further. Flexibility is key for a low-cost energy system, so supply complementarity, in particular solar and wind, but just all the thing on bioenergy, on hydro reservoirs, that's very valuable. Then grids are very important. We need more grids, and in particular also more interconnection grids from region to region, country to country, more demand response. Just think on smart EV charging, district heating, where electricity can be brought in, and other kinds of demand response. Curtailment is always part of a low-cost solution. 3, 4, 5% of all electricity might be in the end curtailed, and storage. Hydrogen, the hydrogen hype blocks the view on the real solutions. Due to the direct electrification, it's simply better, lower in cost. However, most of the hydrogen is used for hydrogen to X solutions, and the X is typically heat or e-fuels and chemicals, and that will be largely ammonia, methanol, and kerosene jet fuel. Power to X economy, I would say, is the core characteristic of the energy system. Said that, let me thank you for your attention, and to my team. Without such results would not be possible. So many thanks again for your attention.